a multi-stage data attack traceability method based on convolutional neural network for industrial Internet. Abstract. In order to accurately define the network area to which data attacks belong and avoid multi-stage delay in industrial Internet, a multi-stage data attack traceability method based on convolutional neural network is proposed for industrial Internet. The convolutional network is used to solve the training expression of the classifier, combined with the multi-stage attack data and information samples of the industrial Internet, improve the expression conditions of the encryption algorithm, and realize the construction of the multi-stage consensus mechanism of the industrial Internet, define the value range of multi-stage data of workflow meta-industrial Internet, so as to determine the function of the traceability automatic capture mechanism on data samples, and complete traceability of multi-stage data attacks of industrial Internet. The comparative experiment results show that the proposed method can accurately define the sample interval of data attack behavior in the 6 network regions selected in this experiment, and has strong practical value in solving the multi-phase delay problem of industrial Internet. Keywords: convolutional neural network, industrial Internet, data attack, classified training, metadata, automatic capture mechanism, network area, multi-stage delay. Introduction. Convolutional neural networks have been widely used in various machine learning tasks. In the process of updating the neural network parameters, the gradient of each layer of the network is obtained by using the backpropagation algorithm, which is the chain rule of the neural network. Tracing the big data model processing process can help to evaluate the data quality and reproduce the data generation process. When a certain result data is suspected, its source can be traced and traced through audit. If there is an error in the data, you can locate the location and cause of the error, and finally each data can be relied on as an important means of data analysis. Traceability can help decision makers remove noisy and useless data and maximize information decision-making. The traceability technology has been widely studied in fields of database, workflow and distributed system interaction, but the traceability based on big data model analysis is still a great field worth exploring. Traditional traceability methods are mainly applicable to databases or data warehouses, but not in the field of big data due to its diversity, heterogeneity, large scale and other characteristics. Data traceability is information about source data and data creation process which can be used to evaluate data quality, audit and track data sources, and quickly locate the location of errors. At present, there are many researches on data traceability in the field of database, but few in the field of big data. Multi-stage data attacks on the industrial Internet will affect the stability of the network operation, which will not only cause the network system to show multi-stage delay, but also make data samples unable to be transmitted to the correct node units. In order to avoid the occurrence of the above situation, a multi-stage data attack traceability method based on convolutional neural network is proposed for industrial Internet. On the basis of establishing the multi-stage consensus mechanism of industrial Internet by using convolutional neural network, the data traceability framework is constructed. By defining workflow metadata, the automatic traceability capture mechanism is improved so as to realize the smooth application of the multi-stage data attack traceability method of industrial Internet. Multi-stage consensus mechanism of industrial Internet. As the basis for tracing data attacks, the multi-phase consensus mechanism of the industrial Internet includes three execution processes: convolutional, neural network construction, classification-focused training, and encryption algorithm improvement. This chapter will focus on the above contents. Convolutional neural network. Convolution neural network (CNN) is a multilayer feedforward neural application network. Each layer uses a set of convolution checks for multiple transformations. Convolution operation is helpful to extract useful features from locally related data and distribute the output of convolution kernel to nonlinear processing units. This nonlinearity generates different activation modes for different reactions, which is helpful to learn the semantic differences in images. CNN is specially designed for processing data samples. Therefore, neurons in each layer are organized in the three dimensions of height, width, and depth, just as information parameters in data samples will distinguish different definition values. The important attributes of CNN are hierarchical learning, automatic feature extraction, multitask processing, and weight sharing, which are mainly composed of convolution layer. The increase of neural network layers produces a large number of parameters, and CNN uses the weight sharing mechanism to control the number of parameters. Assuming that the weight of each neuron connection data window is fixed, the number of parameters can be greatly reduced. Rough parameter sharing. It is generally understood that scanning the image with the same filter is equivalent to feature extraction once, thus obtaining a feature map. The parameters of the filter are fixed, so each different area of the data sample is scanned by the same filter, so the weight values are the same, which is called weight sharing. Fig. E shows the classic CNN structure applied in the traceability method of industrial Internet multi-phase data attacks. Classical CNN structure of convolutional neural classified training. The transition from source model to intermediate model is a typical transfer learning based on convolutional neural network. The combination of pre-training model and layer freezing method is used for the construction and training of CNN model, including the following key process. Initialization stage. Retain the weight parameters of the pre-trained CNN model as the feature extraction source in the first stage of model training. Load the parameters and weights of the pre-training model other than the last fully connected classification layer. Freeze the convolution layer and pooling layer of the pre-training model, and only train the new classifier layer. The second stage. Transfer the reserved parameters of the convolution and pooling layer of the pre-trained model on CNN model, and dock with the new fully connected classification layer trained in the first stage before, to obtain the intermediate model. Convolutional neural networks usually freeze the weights of the first layers in the pre-training model, and then use the data from the target domain to retrain the next layers. This process is called fine-tuning. The purpose of fine-tuning is to extract high-level features of the target domain, reduce the content difference between the source domain and the target domain, and improve the model recognition rate. In general, increasing the number of network layers can help extract more high-level features. Therefore, it is considered to appropriately increase the number of network layers while conducting migration learning, that is, to add an adjustment module, so that the model can obtain the unique, higher-order, statistical features of the target domain. The weight value calculation results based on the data samples of the front layer and the rear layer are shown in Formula R and Formula 3. Encryption algorithm. The multiphase data encryption algorithm for industrial Internet based on convolutional neural network involves public key and private key, which are selected and saved by users themselves, and can be transferred to anyone. The public key can be calculated through the private key, but the private key cannot be calculated in polynomial time through the public key. The public key crypto system can be used to encrypt messages. The sender uses the public key to encrypt the message to get the ciphertext. After receiving the ciphertext, the receiver uses the private key to decrypt the ciphertext to get the plain text. If the subkey exceeds the threshold value, the whole plain text can be recovered. If the subkey is less than the threshold value, no information of the whole plain text can be obtained. No master key information can be obtained through the subkey. Let represent the key threshold value in the first encoding process, and represent the key threshold value in the second encoding process. The value relationship between the two satisfies the specific definition of threshold values, and is Formula 5, where represents the ciphertext transcoding coefficient, represents the ciphertext sample value in the first encoding process, and represents ciphertext sample value in the second encoding process. In order to establish, it is required that the values of end indicators should meet. Data attack traceability scheme. On the basis of convolutional neural network, a data traceability framework is constructed, and then the automatic traceability capture mechanism is improved by defining workflow metadata, so as to achieve the smooth application of the traceability method of industrial Internet multiphase data attacks. Data traceability and tracking framework. The core of data traceability is traceability metadata. Any traceability system needs to manage its traceability information well, which inevitably requires an overall traceability framework. The traceability of industrial Internet multiphase data attacks was first developed in the database field, which specifically refers to scientific databases or regulatory databases. That is, such databases need to be annotated under special monitoring management. These annotations are authoritative descriptions of professionals and have a wide range of applications. For example, an encyclopedic database such as Wikipedia needs a large number of professionals to edit behind the scenes. And finally, the content presented on the network will contain a large number of other database information. So this regulatory database brings about the problem of data ownership. The traceability methods in the database are mainly annotation method and inversion method. The annotation method records and stores data items and transfers them together with the data. The inversion method does not need additional storage. and directly C. Unstructs the inversion expression for reverse tracking. Workflow metadata. The previous section has introduced the data traceability framework, which is designed to ensure the execution of tasks. However, the actual traceability does not require all its data. The key is to extract the relationship between models. The workflow metadata is designed for traceability. It mainly includes the global basic description of the workflow and the dependencies between models. The details are as follows in the industrial Internet multi-phase. Data tag behavior represents the global description of the model workflow, as shown in Table E. Table E. Workflow model of data tag behavior. Mechanism. Coarse grain traceability of multi-stage data tags on industrial Internet will later process traceability, which is caused by black box effect in workflow, because the processing algorithm in any workflow system is transparent to users. As far as workflow process management is concerned, this will undoubtedly reduce the burden on users. However, for traceability management, encapsulation will mean shielding the details. The general workflow traceability model can only be represented as process-level traceability, that is, coarse-grained traceability, and has no knowledge of the process of nodes, which will inevitably lead to the dependency differentiation problem of data items. That is, it is impossible to analyze the exact source item of a certain item in the result data. Traceability system, including coarse-grained traceability, fine-grained traceability, and traceability diagram display. The coarse-grained traceability function is based on the traceability metadata and aims to track users' needs at different levels, including tracking the data source according to the result data, tracking its generation process according to the result data, tracking its source according to the intermediate data, and storing the traceability mapping sequence. The data targeted by this process are all file level. The fine-grained traceability uses a recursive method to track data items in the result file. Its implementation depends on the underlying Hadoop extension, mainly including the capture and storage of traceability information in the map and reduce processes. The traceability map display function mainly displays the traceability information in a visual form. Experimental process accuracy of the selected traceability method. S. Definition of the sample interval of industrial Internet data tags can affect the probability of multi-stage delay in the network system. In general, the higher the definition accuracy is, the lower the probability of multi-stage delay. On the contrary, the higher the probability ensure the data quality after big data platform processing and the process of debugging result data generation. The introduction of data traceability is necessary. Therefore, the traceability of industrial Internet multi-phase data tags based on convolutional neural network is a topic worthy of research. Firstly, the traceability information metadata model of the model workflow is designed, and a data sample traceability method based on convolutional neural network is proposed. Based on this metadata model, and the advantages and disadvantages of this method are analyzed. Secondly, specific traceability objects are discussed. According to the situation, Finally, the whole industrial Internet environment is tested, and the feasibility of the system and the effectiveness of the traceability method are demonstrated through experimental analysis, and the expected goal is finally achieved.